Look around wherever you are right now. The chair, the air, the water in your bottle, all of it is matter. And chemistry begins by sorting that variety into a few useful categories. Over the next few minutes, we'll cover the physical states of matter, mass versus weight, conservation of matter, how to classify a sample, and atoms and molecules. Matter is anything that occupies space and has mass. Solids and liquids are obviously matter, but gases count too. If gases didn't take up space, a balloon would never inflate. On Earth, we meet three common states. A solid is rigid and has a definite shape. A liquid flows and takes the shape of its container, but forms a flat or slightly curved upper surface when gravity acts on it, and has a fixed volume. A gas takes both the shape and the volume of whatever contains it. A fourth state, plasma, is a gaseous state containing appreciable numbers of electrically charged particles. It occurs in stars, in lightning strikes, and in plasma torches used to cut metal. Now, a distinction that trips up almost everyone. Mass and weight are not the same thing. Mass is a measure of the amount of matter in an object. Weight is the force that gravity exerts on it, and it's directly proportional to the mass. So, on Earth, the two track each other. Send an astronaut to the moon and her mass doesn't change at all. Her weight, though, is only 1/6 of her Earth-bound weight, because the moon's gravity is 1/6 of Earth's. And during the trip itself, when she experiences negligible external forces, she may feel weightless. But she is never massless. If mass measures how much matter is present, what happens to that amount when matter changes? The law of conservation of matter says there's no detectable change in the total quantity of matter present when matter converts from one type to another in a chemical change, or changes between solid, liquid, and gaseous states in a physical change. Think of it like a sealed box of Lego bricks. Pull the model apart, rebuild it as something completely different, and if nothing leaves the box, the number of bricks and the mass stays exactly the same. That's brewing. Glucose turns into ethanol and carbon dioxide, and the total mass doesn't change. So how do we sort a sample of matter? Two questions do the whole job. First, does it have constant properties and composition? If not, it's a mixture, two or more types of matter present in varying amounts, whose components can be separated by physical changes such as evaporation. If it does, it's a pure substance with a constant composition. Every sample of sucrose is 42.1% carbon, 6.5% hydrogen, and 51.4% oxygen by mass. Second question, for mixtures, is it uniform throughout? Italian dressing isn't. One drop is mostly oil, another mostly vinegar, so it's a heterogeneous mixture. A sports drink is uniform in every drop, so it's a homogeneous mixture, also called a solution. For pure substances, the second question is, can it be simplified chemically? Iron, silver, and oxygen can't be broken down by chemical change, so they're elements. Mercury 2 oxide can be broken down by heat into mercury and oxygen, so it's a compound. Zoom in far enough and every element is made of atoms. An atom is the smallest particle of an element that has the properties of that element and can enter into a chemical combination. Atoms are almost unimaginably small. It would take about 7,000 carbon atoms to span the diameter of a single strand of spiderweb. Only a few elements, the gases helium, neon, and argon, consist of individual atoms moving about independently. Most others join into molecules. A molecule is two or more atoms, joined by strong forces called chemical bonds. Hydrogen and oxygen gas are each pairs of identical atoms, while a water molecule contains hydrogen atoms and one oxygen atom. The atoms move around as a unit, much like cans of soft drink in a six-pack, or keys on a single key ring. Let's put all of this together with one example: the decomposition of water. Step 1. Classify the starting material. Water has a constant composition, so it's a pure substance, and it can be simplified chemically, so it's a compound of hydrogen and oxygen combined in a 2-to-1 ratio. Step 2. Add energy from a battery or power supply, and the water breaks down into hydrogen gas and oxygen gas. Both products are elements. Step 3. Follow the atoms. 2 water molecules rearrange into 2 hydrogen molecules and 1 oxygen molecule. We write that as 2H2O liquid gives 2H2 gas plus O2 gas. Step 4. Check conservation. 4 hydrogen atoms and 2 oxygen atoms go in. 4 hydrogen atoms and 2 oxygen atoms come out. Nothing is lost. The atoms have simply been rearranged exactly as the law of conservation of matter requires. Here's one for you. Cloudy apple juice with pulp settling at the bottom. Is it a pure substance, a homogeneous mixture, or a heterogeneous mixture? Pause and decide. Its composition varies from point to point, so it's a heterogeneous mixture, like Italian dressing, not like a sports drink. Let's pull the threads together. Matter occupies space and has mass. It commonly exists as solids of fixed shape and volume, liquids of fixed volume but variable shape, and gases that take both from their container plus plasma at high temperatures. Mass measures the amount of matter and doesn't change with gravity. Weight does. Total matter is conserved in any change, and every sample is either a mixture, heterogeneous or homogeneous, or a pure substance, an element or a compound, built from atoms and molecules. Everything in this lecture comes from section 1.2, Phases and Classification of Matter.